All right, so statics. Has everybody gotten a chance to look at the assignment, look at the vector review? Anybody have any questions about it? I'm going to spend today just sort of going over what I consider to be for this class, the most important points from the vector review. But before I start, does anyone have any questions you'd like me to go over? Or? Okay. So the vector review. The first thing is from physics, you're probably more used to seeing the notation something times I plus something times J, and then maybe plus something times K. We're just going to use this new notation. There are mathematical reasons that this is a useful way to write this. It makes it possible for you to use matrix math with vectors. So all this means, this notation that might be new to you is the top element is the x component, the middle one is the y component, and the bottom one is the z component. And if you see just two like that, that means just the x and y components. And you should always think of this as equivalent to A, B, and then just 0 for Z. Okay? So these are vector components. In order to express any vector in components, you always first need to define a coordinate system. When you've done vector stuff in math classes, if you've done math classes with vectors, this fact is kind of glossed over because mathematically speaking, there's no real reason to think about what the orientation of a coordinate system is. The orientation of a coordinate system is a relationship with the actual physical world, you know? You say like, okay, I want my coordinate system x-axis to be lined up with the ground or something, okay? Mathematicians don't believe in the ground or whatever, so you know, they don't care about that. Okay, so, but the first thing you have to do is define a coordinate system. So that's CS, coordinate system. So like, for example, if you have a vector that has a length of 1.5 and makes an angle of 30 degrees with the horizontal, what are the coordinates of that vector? What are the components of that vector? Well, it depends on the coordinate system. So if your coordinate system is this, where this x-axis makes an angle of 30 degrees with the horizontal, then that whole vector just lies along the x-axis, and the components would be 1.50. Okay. If you're using the coordinate system that you're most familiar with, like this, then the components would be 1.5 times cosine of 30 degrees, 1.5 times sine of 30 degrees. So that's like 1.299, 0.75. it always works to find vector components to go find the counterclockwise angle theta from your coordinate system's positive x-axis to the vector. And then the components are the length of the vector times the cosine of theta and the sine of theta. So I know you're probably, you're used to, like, what are the components if this is the coordinate system? What are the components of this vector? You're used to thinking of this probably as a right triangle. Well, let's say the length of this vector is 10. Okay, and then you do trigonometry to get the legs of that triangle, and that works fine. So this length would be 10 times the cosine of 40. This length would be 10 times the, I did that backwards. This would be 10 times the sine of 40. This would be 10 times the cosine of 40. You know what quadrant you're in. And so the components here are negative 10 times the sine of 40 degrees, negative 10 times the cosine of 40 degrees. But you always can just say, okay, well, the counterclockwise angle from the x-axis is 90, 180, 270 minus 40, And so the length of the vector is 10, so this is 10 times the cosine of 230, 10 times the sine of 230. And so that way of doing that calculation is always there, and it'll do the plus minus signs for you, Okay, once you figure out the components of a vector, it makes calculations easy. I want to point out that entering vectors in TI calculators is pretty easy. Unfortunately, every model of the TI calculator, you pretty much have to do it differently. Okay, so entering vectors or vector components in TI calculators. So if you have, I think, a TI-83 or a TI-84, some TI-84s you have to do it this way, some it's one option. You go to matrix, so I think you go to like second function and then go to math or something. There's that lets you into the matrix environment. And then go to edit. And then you want to enter a 2x1 or 3x1 matrix, depending on whether you're doing a 2D vector or a 3D vector. Okay. And then you just enter the values. And then you have a variable that has that vector, those vector components in it. If you have a certain TI-84s or 86s or 89s, you can just enter a vector as, so square bracket to start the vector, then another square bracket to indicate a row of this matrix. Like this is just the matrix notation. So you'd go like A, and then that's the end of the first row because we just want a column matrix. And then the next row is just B. The next row is C. And so that's how you enter a vector. And then you can store it in a variable name. So use the store function and give it whatever name you want, U or whatever, you know. Then some other TI calculators, 89s let you do this. I think maybe only 89s now that I think about it. Let you cut down a little bit on the number of keystrokes by just going A, semicolon, B, semicolon, C, end matrix. So in this notation, commas separate values in a row and semicolons separate rows. So this is a column matrix. And again, you can just use the store function. And then the last one, if you have a TI Nspire, you go to, I don't have one with me, I sort of forget what this button looks like, but there's a button that looks like elements of a matrix, you know. So you go to this, you enter the size of the matrix you want, and then just enter the values. So fiddle with your calculator, see if you can figure out how to do that, and then let me know if you have trouble figuring it out. Once you get used to it, it's really easy on all of these. This one is, if you have an 83 or an 84, it's like a finger workout. It's like very clicky, but you know, anyways, it's not hard to understand. It's just like menu, 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 like it's sort of annoying. The 89 is actually my favorite. Okay, and then once you, like, why would you enter those? Like, you could enter it and just look at how nice a matrix looks typed, but that's not really the point of it. So calculations that we're going to need are adding two vectors. And the way this works is if you're adding this plus this, the answer is this. And in a TI calculator, you can just use the regular add function, and it'll do that if you have your matrices entered. So you're just using the plus. To multiply a vector by a scalar, by a number, so a scalar, that just means a number. So if you want to multiply like D times the vector A, B, C, that just gives you an X component of dA, a Y component of dB, a Z component of dC. And in a TI calculator, just use the regular multiplication button. To calculate the magnitude of a vector, that's just the Pythagorean theorem. And so if you have a vector u that's equal to ABC, the magnitude of that vector u, and you denote that as an absolute value of a vector. This vector symbol looks funny. Let me make that better. And it's just equal to the square root of the x component squared plus the y component squared plus the z component squared. If any of those components are negative, the squared makes it positive. Okay, in a TI calculator, some TI calculators, if you're lucky, they have a built-in function for this. I think it's 89s and Inspires have this function built in. And that function is called norm. So if you want to calculate the magnitude of the vector 3, 4, 0, type it like this, and it'll give you the answer, 3 squared plus 4 squared square root is equal to 5. Okay? If your calculator doesn't have that, it's easy to enter these programs, and you don't have to. You can get by fine without it entered, but if you think this stuff is kind of interesting and you want to save a little time over the course of the class, all of these things I'm talking about, if you look at that textbook in D2L, there's code for entering these programs, and it tells you how to get into the programming environment and stuff, and it's easy to enter programs like this on your own. So if you have an 89 or Inspire, it's already built in. If you have an 84, 86, 83, you can program it quickly, and then you have it, and you use it basically the same way as this. Okay, the fourth thing, now we're getting into some things that maybe haven't been so useful to you in the past, but in this class, you're going to use it all the time. Calculating a unit vector in the direction of a given vector. Okay, well, I'm going to tell you how to do this, and I'm also going to give you some notation for this kind of stuff. So say that our given vector is, again, u, and it has components A, B, C, and we don't know what the magnitude is, but we're assuming that it's not 1, so maybe it's 50 or something, If you calculated the magnitude of this vector, let's say it gave you the answer 50, okay? And what we want is a vector that's in that same direction, but if you calculate the magnitude of it, it gives you 1. That's what a unit vector is, okay? So notation-wise, what we're looking for is a vector u hat. that hat means it's a unit vector. It has a length of 1. Okay? So the variable name is the same. I don't know why I keep writing these things so funny looking. It's just U with a fancy hat now. It thinks it's fancy. Okay, so how do you calculate that? U hat is just equal to 1 over the magnitude of the vector times the vector. In other words, since our vector has components A, B, C, you can calculate this unit vector as 1 over the square root of A squared plus B squared plus C squared times the vector components A, B, C. Okay, so I guess I might as well go one more step. The x component then is A over that square root. The y component is B over that square root. And the z component is C over that square root. It seems like sort of a random thing to want to calculate. Can anyone think of a case where you would want to calculate a unit vector in the direction of a given vector? Okay, so think about the force that a cable applies to something. I know this is a while ago or whatever, but see if you can. So if you have a cable applying a force to an object, okay, so let's say we have, you've seen it in cases like this. So you have some rolling object on a ramp with a pulley, something like that. Okay. What's the direction of the force that cable applies to the cart? Okay, you have a weight force going down. You have a force pushing on the ground, okay, from the ground. The force applied to this thing by the cable is parallel to the cable. We don't know the magnitude. It has a magnitude of t, right? Okay, well, if this is at a funny angle like this, how are we going to come up with a vector that has a magnitude of t and is in this direction? The answer is we're going to use the coordinates of where the pulley is, the coordinates of where this is, to come up with, like, usually coming up with a vector that's in the direction of this cable force is not that hard. You can use other coordinates to come up with that, and I guess I'll talk about that in a second, but the problem is that vector you come up with doesn't have the length t, right? So how do you give it the length t? You first come up with a unit vector in that direction using this approach here, and then you multiply that unit vector by t. And that's a vector that has the magnitude you want and the direction you want, okay? So, and in fact, that's what you would do for this, to come up with this normal force too. You could come up with the direction and then get a unit vector, multiply it by n, and then that would let you calculate those forces eventually, those force vectors. Okay, so you haven't done very much of that in Physics 1, but we're going to do that all the time, and you're going to get very used to that. Okay. Okay, so the idea here is that this force vector is t times some unit vector. Okay. In a TI calculator, how do you do this? If you're lucky and you have TI 89 or Inspire, there's a built-in function, lowercase unit, uppercase V, and you just enter your vector. And so let's say, let me use the same vector just because I can do it in my head. So let's say we have a vector -4, +3, 0. Okay. Well, that with its hypotenuse makes a 3, 4, 5 triangle, so it's easy to do the math. The magnitude of this vector is 5, right? Divide every component by the magnitude, and you come up with the vector -0.8, +0.6, 0, if I'm doing that math right. And that is a unit vector, and it's in the direction of this original vector, -4, 3, 0. Okay? Pretty great, right? Since this is something we're going to use a lot, if you have one of these calculators, get used to using this function. It's nice to just automatically remember to use this function instead of going through all the calculations yourself. If you have an 84, 86, 83, I think it's probably worth looking at how to enter this into your calculator. Basically, the first time you enter a program into your calculator, it takes a while to get the layout, understand the layout and everything. And then the second time, it doesn't take as long, and then it's really fast after you get used to it. But please come talk to me if you want help entering any of these things. I'd be happy to show you how to do that. I think, how many of you guys have taken like programming classes yet? A few, half-ish. Well, I mean, I think this is one of the nice things about this is it just gets you sort of used to the idea of programming, you know. And the hardest thing about any programming class, any intro programming class, is getting the idea of programming, you know, just understanding like when a program is going to work, when you haven't given it enough information. And I think it's sort of helpful doing these sort of simple programs just to get used to that process, you know. When I was in college, I did an internship one summer at Iowa State, and I was working with these engineers, and I was kind of like new to programming. I think I'd taken 2 programming classes, and I was talking to the guy who was like the leader of this research program or whatever, and he was, I asked him something about the program I was writing, and he was like, "Oh, what language are you using?" You know, and whatever it was, I think it was C. And so he like wrote something and was like, "I think it's like this, blah, blah, blah," you know. And I'm like, how many programming languages do you know? You know, like he just pulled that out of, and he's like, I mean, I guess all of them, you know? And I was just like, whoa, that's amazing. But like, once you get used to, once you've done a couple, you know, it's just sort of like all the same. There are little tricks here, little differences between object oriented and whatever, but like, yeah, really, like once you get used to programming, the idea of programming, it's really just learning what command is the same as this command and this one, you know. Anyways. Okay, so that's some stuff that you're going to need to do. Then there are two ways to multiply two vectors together, and both of them are going to be important in this class. Can you think of what those two ways are? Yeah.
Dot and cross.
Yep, dot and cross. So this is multiplying two vectors. Cross is going to be much more important to us than dot, but we'll use dot sum too. So there are two ways. The dot product and the cross product. And the most important thing to remember about these is the dot product. The output of a dot product of two vectors is a scalar. It's a number. And the output of a cross product is a vector. Okay, so the first one is dot product. So the dot product of a vector ABC times a vector DEF is an X component AD, a Y component BE, and a Z component CF. What am I doing?
Add it together.
Add them together. That's what it is. What I said before was not right. Okay, so that's a scalar. This is just a number. In a TI calculator, if you have an 89 or an Inspire, there's a function lowercase dot, capital P, let's make this one 3, 2, 1. And if you enter this in, it'll spit out the answer 10. So 1 times 3 plus 2 times 2, so that's 3 plus 4 plus 3 is 10. On all calculators, if you enter the first vector as a row vector, so by that I mean a 1 by 3 matrix, and the second vector as a column, so that's a 3 by 1 matrix, you can just use the regular multiply button. And that's because, so by the rules of matrix multiplication, if you have a matrix 1, 2, 3, and you multiply it by a matrix 3, 2, 1, that gives you the dot product of those two vectors. This would give you 10. You also can just enter a dot product program in your calculator. And there's instructions on how to do that on D2L. Yes?
What would happen if you entered both vectors as row or column?
And just used multiply, it would give you an error.
Okay.
It doesn't know what to do yet. Okay, so some things to notice about the dot product, some useful facts. And by the way, when I write these notice things, a lot of times these are things that I use in the lecture quizzes. So pay attention to those as you go through your notes. So first, a lot of times, often, the dot product is called the scalar product. Why would that be?
The output is scalar.
Right. And so we're going to, see, as you would imagine, that often the cross product is called the vector product. Second, two vectors that are oriented within 90 degrees of each other have a positive dot product. So, for example, if you had a vector like this, and you took the dot product with a vector like this, you can see that those are less than 90 degrees apart if you put them tail to tail. And so this would give a positive dot product. If two vectors are more than 90 degrees apart, so two vectors that are greater than 90 degrees apart have a negative dot product. So an example of that would be if you have a vector like this and you take the dot product with a vector like this, you'd get a negative dot product. Probably the most useful thing about dot products is that if they're perpendicular to each other, as you might imagine from these two facts, the dot product is 0. So two perpendicular vectors have 0 dot product. I said that the dot product is often called the scalar product. It's also sometimes called the inner product. Based on these last 3 facts, can anyone think of why it would be called the inner product? It's because in some sense it tells you to what extent two vectors are in the same direction. Okay? They're like in the same club or whatever. They're in the in crowd, you know? We're going to see that the cross product is 0 when vectors are in the same direction. Whenever they're parallel, 0 cross product. It has the biggest magnitude when they're perpendicular to each other. And so sometimes cross product is called the outer product. Okay, it's seeing how far out of the same line or whatever the two vectors are. And then the last fact, this is a lot of facts. But the last one is that order doesn't matter for the dot product. So if you take the dot product of A and B, you get the same thing as if you take the dot product of B and A, B dot A. All of these are really, in a way, all of these are just sort of contrasts with what we're going to see with the cross product. We're going to see that with cross product, the order does matter. A cross B is not the same as B cross A. And two parallel vectors have a 0 cross product. Okay, so now let's talk about the cross product. This is the one that's going to be more important to us. So if you have the cross product of A, B, C, and D, E, F, the X component, so to come up with the X component, you cross out the X values, the X components of the two vectors, and then you take this times this minus this times this, okay? That's where the cross comes from, okay? And so your X component would be BF minus CE. You do the same thing on the Y component. Cross out the Y components. Take A times F minus C times D. But you have to be careful with the Y component. So let me do that first. The Y component has this little wrinkle thrown in. So it's going to be A times F minus C times D. And then you make that whole thing negative. Y components always have to be they just have to be a little different. They can't ever follow the crowd. So always, anytime you do vector calculations, ask yourself, like, is there some weird thing with Y that I have to take into consideration? And then Z, cross out the Z components, and it's A times E minus B times D. what if you have the vector AB crossed with, let's call it CD? Okay. So first of all, remember this is AB0 crossed with CD0. So use this same procedure here. Cross out the x components. B times 0 minus 0 times 0 times d. So the x component is 0. Okay. The y component, cross out the y components. A times 0 minus 0 times c. So the y component is 0. Okay. And then the z component is a d minus b c. Okay, this is something we're going to use a lot because we're going to do a lot of calculations in the xy plane. So notice that this only has a non-zero z component. Uh-oh. I think my pen's running out of juice. I just have to charge my pen for a second. Let's see.